Swayam Prabha. Digital India. Educated India.
Is I wanted to do one problem in this was impulse based system, and one in pressure based and one in dynamic. So far we've seen an impulse based system using the RMF, maybe we can just call it the RMF method. There's no, you won't find these things in books a whole lot. Even if they do, they'll talk about a concept, and then the closest I came to find is in one of the books somewhere they talked about this. I don't know if they even called it the response modification factor, I forget, but no detailed design examples presented or anything like that. So you don't have to feel left out. Even civil engineers might feel left out. But maybe if you have to supervise a design for a machine structure and there's masonry in it, make sure you have reinforced masonry. We'll talk about it. So this is a masonry wall made up of have you heard of CMU? These are concrete masonry units. I've seen quite a bit of it here, so I don't think it's uncommon. I don't know what it is called. Is it called CMU here or blocks, concrete blocks? Yeah, blocks. Aerated autoclave concrete, right? AAC blocks, correct. So these blocks, if you see, this is a cross section and it will have a hole. So this is the concrete block and this is inner part is hollow. Typical blocks, these are nominal units, so these are 8 inches, and we have 8-inch CMU blocks, and this is also 8 inches. So when you have a wall, and of course it depends on, so these blocks would be something like this, and we also say this is your wall. So you can have a reinforcement in this. So this is reinforced concrete masonry unit. The reinforcement will run through all the way, and you won't reinforce every unit of it. You might reinforce. So that's also the design part of it. So this is nominal 8 inches, this is 8 inches, and so the reinforcement is running through maybe every third, every fourth, whatever the case may be. It's given that the height of the wall is 16 feet and it's 1 story. Masonry can go to 3 stories on their own, reinforced. So this is 1 story, and 220 pounds TNT at 50 feet from the wall. Properties of the masonry are you have now instead of FC prime, it is a masonry. There are a lot of factors that go into determining these properties, but let us keep it simple. Masonry units, concrete, if it is 4 KSI, this is 1500, so about 1/3 or between 1/3 and 1/2, and the modulus is also of the same number, but an order PSI to KSI. Just as a comparison, concrete is 4 KSI and 3600 KSI. This is just a comparison. Bars are still, we use 60 KSI. Now, the properties of this masonry are the net area is 0.49 square inch per foot. The IG, because they are cut to certain dimensions, all these are from tables, 351 inches per 4. So, the moments of inertia is given, and the crack moment of inertia is also given. For here we are not engaging in those calculations. You are asked to determine, and the self weight masonry is 16, the roof, this is for the roof. So, roof, so there is a roof here. So, this is 69 pounds per square foot for the roof, plus masonry itself is 40 pounds per square foot, plus any additionals you could have. That number just depends on additional dead loads, such as you might have waterproofings and other such things on top that you could add. So, all of it, let us say, is given to be 112 pounds per square foot. What is the question? Is the wall safe? Which area? 0.49. This is per square foot. So, the whole is taken out, right? The whole dimensions are taken out. I do not know if it is per square inch or per square foot. Let us see, I do not know if we need that information anyway. And another information, yeah, I see what you are saying. This seems low. The other thing is it is reinforced at using with number 5 bars, which is 5/8 inch in diameter, at 24 inches center to center. So, basically every third one. So, let us start with the blast load parameters. You have Z is W, sorry, other way around. R by W power 1 by 3. So, this is 50 feet, 220 pounds, comes to 8.23. And the pressures are 37.9 psi, IR is 136, and TD is 2 IR by PR, which is 7 point. Consequently, P naught is PR multiplied by B multiplied by H. So, this is per foot, 37.9 multiplied by 12 inches, and the height is 16 feet, comes to P naught is equal to 87.3 kips. Then our next step is our wall section capacity. Masonry, your strength increase and dynamic increase factors are 1.0 on flexure, DIF is 1.17 in flexure, and steel, the SIF is 1.1, reinforcement DIF is also 1. So, this is 1.19, sorry, and this is 1.17. So, here from FM prime dynamic is SIF multiplied by DIF multiplied by FM prime, which is 1.96 KSI, and here FY dynamic is the same thing, and that value is 77.2. What's the highest grade of steel now? We have now reinforcement there, 60 KS, not 60, 80 KSI, 100 KSI. That is, here what are the higher grade steels? 80? 600 MPa, for 415 and 600, those are the two. In reinforcements, those two steels. Yeah, you know, that's something also to see if the effect of, we looked at it, the effect of using high strength concrete and high strength steel, whether those things help. We could look at, maybe that could be a tutorial problem we can look at. But we don't have, some of them we don't have the DIFs and the SIFs for it. Then calculate Mn and Rn. You don't need the remaining moment capacity here. This is a wall. Those are only for roofs that you need to do the remaining moment capacity. So, the way it is designed is, suppose you have the reinforcement here, and the reinforcement is typically you grout it. Grout properties are not quite considered, so you would grout it, and you have here, this is 8-inch nominal, and but the design is only 7.62 inches, and the D here is considered from here to here if the wall pressures are applied this way. So, the D is right down the middle, So, D is nothing but h by 2, which is 3.81 inches. AS is given, it is a number 5 bar at 24 inches center to center, and the area of a number 5 bar is 0.31 inches square inch every 2 feet. So, AST is half of it at point square inch per foot. Then we calculate, so this is 1 second, then we calculate the, what A we call it the Whitney stress block depth, and you can substitute the methods you use here for the codes in this case. So, A is given as AS Fy dynamic divided by 0.85 Fn prime B. So, comes to 0.155 77.2 divided by 0.85 times 1.96 multiplied by 12. So, here you see it is actually very small. Then the fourth thing is Mn is AS Fy dyne multiplied by D minus A over 2. So, same numbers if you use comes to 3.5 kip feet per foot of the wall. And then the required Rn for this is a uniformly distributed load and simply supported. So, for these conditions this is 8 Mn divided by L. So, 8 times 3.5 by 16 feet, and Rn comes to 1.75 kips per foot of wall. Do you all use OneNote for taking notes? What software is there? Anybody takes notes on electronic iPads or no? Nobody? OneNote? You use OneNote? Yeah, even I use, the only reason I use the software is if I put a rectangle, it'll OneNote. Oh, it is? I have to search for it. I've got to find out. Maybe I'll shift my oh, I have been searching, but you know these things are kind of hidden and you give up after a while, after a little bit of search, not a deep search. So, step 3 coming with all the process is the same, dynamic properties, and so we start with I average. There they will give you these values in a table for different block sizes. So, that is very convenient, and ME is KLM, so which is 0.78, and the mass is we calculated 112 pounds per square foot. So, basically it is 112 kips per foot multiplied 1 feet of the wall multiplied by 16 feet, and So this comes to multiplied by 1000, so consistent units 3.63. And so KE is 384 EI pi. Now this is uniformly distributed. So 5L cubed comes into play here, and we have all these numbers. E is remember E is again not changing with, so 1500 KSI divided by 5 times. So KE comes to 3.08 kips per inch. Tn is point or 216. It's a small short problem, milliseconds. Then the last step is the wall response. Again TD, this is also an impulsive response. A lot of our durations are very short, and the TNs are, we have seen TNs in the ranges of 155, 200s. The lowest we've seen is 66 milliseconds. So many of these, even if your load duration is under 10 milliseconds, for you to get over to the next, it is you'll see all of them are tenths of what the natural time period here is. So this is 7.18 divided by 216 is 0.033, is less than 1. Then for a low level of protection, remember, lower the level of protection, higher the theta, higher the allowable rotation, support rotation. So we calculate mu, which is KEL divided by 2, our Rn was 1.75 kips per foot. So Rn tan theta, so which comes to 3.08, 16 divided by 2 times. So again mu is quite high, 23.7. Then the last step is check required versus available. See, in all of this, clearly we do not know anything for certain. The approach that at least we take there, and some of you might consult in this field, is that you need to have some established procedure. I mean, that's not what we talked about it in day one. You cannot promise something to your client. Here, all you are doing is to have a procedure, multiple ways, and then come up with the best.
Similar to like as we did in concrete, or
Yeah.
whether it's a steel or any other material, they have changed only material parameters.
Yeah.
But machinery is an entirely different thing. So whenever it's going to fail, it will fail at joints.
Yeah. So here we are not. So that's why the reinforced masonry is there. We have not looked into that. If you're that also sort of leads up to what I said. How do you quantify it, right? How are you going to, is there a process? Yes, the question is a valid question, but how are you going to convert that to a design procedure? The only way you would do it is to, I know, ensure that the blocks are, the integrity of the blocks are there. But if, and you'll find so many structures subjected to these types of loadings. Yeah, that's a good question, open question. We haven't addressed connection issues in even our steel and concrete. Concrete, especially at the corners, a lot of times in cantilevers or any edges, you'll have L shape, right? Now, when you're going to blow out from inside, we are assuming a fixed support, but what's going to happen to that L section? It opens up. So that's actually not good. So connection issues, for example, you might reinforce a column. So this is a side note. So for instance, if this is your regular, right, F4 loading like this, and suppose you have a reverse loading. Now what is it's going to do? So it's going to open it up. So you might change it to something like this instead, right? So when it is going up, this will come into play. When it's coming down, it would close in rather than open up. There are other connection, so that's something we have not addressed, and I'm not sure that the community, at least the private side of engineering community has addressed this also very, very clearly. There's no document that I know of. In seismic, if you see, AISC has a very specific seismic design manual. A lot of the details are addressed in a clear manner. In concrete, there is no, I mean, our committee has a design guide, there are some other books that are available, but there are standards like ASCE 5911 that talk a little bit about, if you see examples, there's no examples on 5911, of course, there are other books. So there's a lot of paucity in literature in all these. And what will they do is they'll punt and say that use seismic principles. Other things that are done, for example, you could design, if you've heard of strut and tie methods, right? In connections, you will calculate your dynamic reactions. And then from, have you heard of strut and tie methods? Yeah, some of you in concrete would have heard of strut and tie. So strut and tie methods are very frequently used in the design of connections. It's a good method to use in blast design. And then how would you reinforce in a strut and tie method? Based on the strut and tie diagram that you are drawing. So your reinforcements could go in the direction of the ties, which are non-standardized apart from your regular. So yeah, once you design of connections is of course in everything, in every, even in simple reinforced concrete, seismic design connections is everything. So in masonry, addressing this, one way to add integrity to it is you have your masonry. So if, let's say I was doing this and I was using these blocks, right? Say every 3 blocks, and I have, then I might say put a sheet at the back, right? This is, could be an FRP sheet. Recommend an FRP sheet at the back. So that way the whole, you're still reinforcing it. So this is your reinforcement, this is your, this is non-grouted, but this is grouted. So that way the whole unit acts as one. Now the FRP is also going to provide you additional capacities, but not an axial capacity, so that's taken out. The stiffness it provides is very minimal. So it could provide additional strength in flexure, yes, but the sheet, then you can do a additional capacity in flexure strength due to the FRP sheets. Yeah, I mean that's I don't know of any other way to. We haven't even, okay, localized damage, right? Just like when you are designing for structures, you also have to design for localized damage. So those considerations also come into play. We are here looking at the overall structure as such. So tomorrow actually we will look into the full structure. There are design procedures for designing for a blast environment, considering the entire structure. So those concepts we'll talk about tomorrow, which are easy to apply. I don't know if that answers your question or not, but that's the best answer I've got.
Yeah, I was thinking whether there is any other methodology.
Polyurea, spray. Two methodologies, but again those designs don't change. These calculations won't change.
That's what I was looking at the principle on.
Yeah.
Whether this is the only procedure we have for designing all these kinds of structures.
Whether if this is the only procedure we have, I don't know, but this is the best I know. So it's I'm limited to what I know. I should look into it actually. It's a good question. I should look into. Yeah. What are you thinking? What's that? Mild steel plate. Well, you're changing properties. Yes, I mean, A, it's expensive. B, it's heavy. Third, how are you going to integrate mild steel plate along with how are you going to connect these plates to the brick wall, right? So that's not a solution I might go with. It's prohibitive in some. It definitely helps in strength, but that's a masonry wall is not for that purpose. But if you're having a hardened, if you're going to protect something valuable, whatever be the asset inside, that's a consideration to have. If you put a small thin mild steel aluminum plate or mild steel plate, how does it add? It becomes a composite structure. There is actually a designs of composite sections. We can do that. Then you get into composite designs for calculation of your moment capacities. Yeah. Any other questions? Okay. So, yeah, keep those questions coming. This makes it quite interesting. Mine often can be a very linear thinking, and this is the only way to get out of the box, asking these questions. So RMF is 2 mu minus 1 divided by mu. So this is 23.7 minus 1. So if you see, this is interesting, right? What do you, wait, no, let's see, can you calculate this again please? No, this is not 1 point, this is not 0.98. What's that? Impulsive loading. So we have the impulsive loading is, pi TD by Tn, right? So this is impulsive loading, sorry. You're right. Thank you. Which means you'll have to help me calculate. So what is it? Can you square root of, is it this 2 mu minus 1 divided by Okay, so what is, if you can help me, 2 times 23.7 minus 1 divided by pi, TD by Tn is 0.033. Okay. How much is that? Fif- 47, 46.4 square root by 46 roughly? Huh? 65.7, okay. Okay, so then the P required is P naught by 65.7 and P naught was 87.3. So how much is that? One point three, 3.2, and provided is Rn is how much? 1.8775. So in this case this is adequate. You can let me also make a mention that you can try some of these out. I think this might be a good, you can try these examples that using, all of these are impulsive loading. The impulse based equation and also non-lin this afternoon. I think, shall we do that? The two examples. Yeah, we can try. Oh, we have another example on masonry today?
Yesterday we had two problems. One of the thing was on masonry. So this we do this.
Yeah,
This yesterday's problem also they could solve completely.
okay.
This
Remaining moment.
remaining moment.
So we can complete that. I think one of these, maybe take the simple masonry one and try that, you know, that I square, what's that, A divided by KLM M,
2 times K.
huh?
2 times KLM.
2 times KLM M, right? So this is RM minus YM minus YE by 2, right?
It's A square.
Huh? A square, I square, A square, yeah. So you try it and compare and see what you get out of it. Okay, final example. This is a concrete roof beam. And we've talked about the roof beam having inbound and outbound. So we're looking at the inbound. So I picked this example because hopefully this is in the dynamic. Let's go, some of these calculations do change. So this is, let's say, the dynamic example or dynamic range example. So, what we have is a roof slab one of the most, especially for me in my academic profession, one of the things that the IIT training helps me most, or I always remember, is which course? Which course in your engineering, if you're working, you think you use the most? The most, top of the list. Huh? Engineering graphics, right? Nowadays, what do? You do by hand or no? It's all AutoCAD or, huh? SolidWorks. Have you ever drawn a line? So we used to have a whole semester of class where we had to draw by hand. All drawings, everything, detailing, whatever. Now, detailing of course was different. Even building frames, there's structures. So with those, I don't know if you've seen T-squares and what is that drawing? With T-squares and drafting, right? You still have those? Oh, you do have it. Good. We've stopped that at least. Huh? You've removed it. We used to have that. What's that arm? What's it called? It's called a drafter. Yeah, we used to carry T-squares. Huh? The other thing is, so that's one of the most, I use it so much. I'm thankful for IIT at that education that gave me the simple but a very effective tool. The other thing is, we used to do truss analysis with drafting. Drafting principles to do all truss analysis. So that's another method we learned, funicular, what diagrams they used to be called. So you just keep drawing diagrams and you get all the, anyway. So this is 6 feet centers. It's a 4.5 inch slab, 14 inches in depth, and span is 30 feet. With TNT of 1,000 again. I just choose some simple numbers for design purposes. Then trying to frame the question. Yeah, okay. The reinforcement is given. That's what I was looking for. So it can have both ways, as we have seen. So the reinforcement provided is, say these are the shear stirrups, and so the reinforcement is 3 number 5s, 5 by 8 inch, and we have, this is 2 number 6s. At the top and the bottom. So 6/8 inch dia and 5/8 inch dia. Okay. So question is the beam adequate? So we've done this, but it's a different regime. So let's see design wise capacities, compare all of them. So, first step is of course starting with the blast load. So, Pi, again no surprise, you have seen exact same numbers to the second decimal before. So, milliseconds. Then go through the member resistance calculation. So, we have seen the reinforcement details. You have 2 number 6s and 3 number 5s. And so, what you have here is a T-beam. So, for a loading like this, sorry. So, we have a T-beam design. With an effective flange width. Without getting too much into it, I will present all the details, but you are finding the depth of the neutral axis. So, the effective flange width is per US codes at least is not greater than the span divided by 4, not greater than BW plus 16 times the thickness of the flange, not greater than the center to center of the joists. And here 72 inches governs. Span is 30 feet, width of the flange is 6 inches. So, width of the web is 6 inches, so on and so forth. But so, BF is 72 inches. Then the depth of the Whitney stress block several things to calculate. Here the dynamic properties Fc prime dynamic is SIF DIF Fc prime, which is 1.1 into 1.19 into 4, which is, and Fy dynamic we have seen is 77.2 KSI. So, the A comes from 0.85 Fc prime dynamic, sorry the other way around. Fy AST Fy divided by 0.85 Fc prime multiplied by B. So, B effective, so here you have 77.2 multiplied, there are 2 bars. So, this is 2 times 0.44 square inches divided by 0.85 times 5.24 multiplied by 72 inches. So, comes to 0.21 inches, which is less than your thickness of the flange. So, assumption is okay. And finally, your moment capacity is AS Fy T minus. I think by the end of the course we can give you a additional certificate in civil engineering design. So 2 times 0.44 and 77.2, 16.5 minus. So actually in our university we do have at least every year a couple of students who are coming from physics or mechanical or even electrical wanting to do civil engineering, and then we send them through a bunch of some remedial courses and they don't have to repeat the whole process. So then the Rn is 8 mn by L, so 8 by so that's a number that we'd like to hold on to. Then the next third step is the single degree of freedom parameters. Mechanical, civil, even electrical, I think we all do statics. So all these principles are from statics. 72 inches, 4.5 overall. I think, what did I say? This is 12 inches. So I have it as, I don't know what I've said. Maybe. Overall is 16.5. Oh, I have it as 14. Let me make sure the numbers are consistent. So overall is 16.5. So this is 12 inches. Yeah. So this is 12 and 4.5. Yeah. So using statics, parallel access theorem, etc., we can find the Ig. This comes to 7627. Then for the cracked moment of inertia, it's the same process. I think all of you would have, at least from civils, you would have done for, I'll just give the schematic and then skip over the details. If you want it for completeness, I can provide it. So this is, we'll assume a C somewhere here, and your steel is N times AS. The modular ratio is 8. So that's the other thing about things like UHPC, right? Your not UHPC, some of the other concretes, other materials where your high strength concrete, for example, even UHPC, I think what's your modulus is about the same you said, right? Which is kind of surprising. I don't know myself. Mutturaju, I think here. But I think non-UHPC, it's up to at least, it's a function of the strength of the concrete. So you don't find it as a strength, the modulus to be a function of the strength of UHPC? It will vary. 25?
45 to 50.
Oh, 45 to 50 as opposed to? What?
5,000 square root of FCK.
Oh, 5,000 square root. So you have it as 5,000 square root of FCK. For UHPC, it may not be that 5,000 may be different. There's an interesting story about square root of FCK. Do you know that? Why is it? I think I've talked about it, right? No? So historically, if you see, a lot of things even in IS codes is square root of FCK.
Yes.
Do you know why? Why don't they change it to something else? I mean, would you agree with it? I mean, you do your regression analysis curves and everything, you might get FCK power 1 point or 0.35 to be a better fit of the data. But why does everything resort to FCK, square root? Slide rule. The slide rules, if you see those days, all the data were manipulated as square root, 1/3, 1/4. Those were easy calculations. And a lot of these data fit to square root better, the best or whatever. That's historically. It's kind of crazy that we haven't gotten rid of the slide rule, even these days of AI and ML. So, so this is, you can calculate, I'll just provide the equations. BF times C multiplied by C by 2 is NASD multiplied by D minus C. So this is D, we know all those numbers. So this is D minus C, this is your equation, quadratic equation. You find C to be 1.38. And your ICR is nothing but BF C cubed by 12 plus BF multiplied by C by 2 square plus 0 plus NASD multiplied by D minus C square. And so ICR comes to 1780 and I average is 4,000. Then so your KE is 384 E sub C I average divided by 5 L cubed. L is equal to 30 feet. So comes to 27.9 kips per inch. Then we calculate the yield deflection. Wait, have we calculated the capacity yet, or? We did calculate RM, right? Yeah, RM is 24.8 kips. Okay. So the yield deflection delta static is RM by KE. So 24.8 kips divided by 27.9, which is 0.89 inches. Then the mass of the system so remember, include the weight of the slab plus the weight of the beam divided by G. Now, you can calculate these, the weight of the slab and the beam, from the areas. So, comes to, let me just put it, somehow I feel not complete if I don't give the details. So this is the weight of the slab plus weight of the beam approximated to 6 by 14 or 612. So this is 6 inches by 12 inches divided by, so comes to 12,750 pounds if the math is right. So M is 33 and the effective mass is KLM. KLM is in this case 0.72. We've got that 0.72 from yesterday, 75. Is 2 pi square root of, comes to 0.18 seconds or so here you will find either then solve the system or the problem using either nonlinear or the analytical equations or design equations, I should say. They are not quite analytical. So the ductility ratio mu, we are given that theta max is 2 degrees. Can you help me with this calculation? Your mu is, what was that expression, tangent of Rn by Ke or Ke by Rn expression. Basically the delta static expression. What's that? Ke into L by tangent of theta max. So can you help me with this one, please? Ke is 27.9. L is 360 inches by 2 times Rn is 24.8 kips, tangent of 2 degrees. We can even, let's try the other extreme also. So this is for HLOP, I think theta equal to, we can check that 8 degrees or 10 degrees I think. Let's try a couple of combinations, it might be interesting to see that. For concrete 2 degrees theta max. Yeah, I think that it's either 1 or 2 degrees. So No, this is reinforced flexure. Yeah, 2 degrees is for moderate, this is for heavy level of protection. For low level of protection it's 10 degrees. So let's try both, and just curiosity wise, for theta equal to 10 degrees, what do we get? Mu. For the first one? And 8? Okay, thank you. So mu for low level of protection is 7.07, mu for high level of protection is huh? Oh, sorry, yeah, other way around, correct, sorry. So low level of protection is 35.7 and this is 7 point. So therefore P required is P naught divided by mu, let's say, and P naught was how many kips we calculated? Did we calculate that or no? 117 kips divided by 35.7 is how much? I'm sorry. No, there's no units at the bottom. So how much? 3.3. So this is 1, and for the other case, for this is the medium, no, this is the low level of protection, and here we need seven kips divided by yeah, this is mu. Oh, you have to calculate the RMF. Oh, sorry. Yeah, I was going to come to that. I don't know why I skipped that step. Yep, you're right. My apologies. It's getting a little ahead of myself. I have that step here. Okay. So then the next step is calculate the RMF. Now TD by TN is 24.5 divided by 183 is 0.134. So this is between 0.1 less than TD by TN is less than 1. So comes in the dynamic range. So RMF is square root of 2 mu minus 1 by pi TD. Maybe one of you can calculate for LLOP, maybe the side can do, somebody can do for LLOP and here for the heavy, plus 1 minus 1 by 2 mu TD by TN divided, bless you, 0.7 plus So, for mu equal to and is 7.07, RMF equal to TD by TN is 0.134. Okay, I think you have all the values. And for the low level of protection, so each case the P required is P naught by RMF. So P required is 100 and how much did we say, 116, right, was the applied load. What was the applied load? 100 and I know we did calculate it somewhere. Or didn't I show it? Okay, maybe I forgot to put that. So P naught, I have calculated it, comes to 116 kips. And 117 kips. So P naught is equal to Pi multiplied by the tributary area is equal to 117 kips. So this would be 117 divided by 8.764, and this is 117 divided by 20.1, 25, 20, and Rn is meanwhile 24.8. What are these numbers? 117 by 8.764. 30?
13.26.
And this is 2 point something. No, 5 point something. So, given these two, the Rn is 24.8. So, we can say that the structure or the roof has a level of protection in between LLOP. No, actually, not even that. It is. It's over. Yeah, it's over. So, yeah, over. Better than H, yeah. So this things like this give you an idea of how much to protect. Could have asked me what about the remaining moments, and yeah, we didn't do that here. But anyway. So I think with that we come to a conclusion of the design aspects. Just a quick summary of the design aspects, at least the methods. So the summary of the methods covered for design. One was for impulsive response, the direct equation approach. So you determine it, and that I square A square by 2 KLM M is RM. Then the response We established the response modification factor approach for all three responses. Allows us to find a capacity. If you don't have a capacity, it allows us to find a capacity to be designed for, and then of course use non-lin in conjunction to establish limits, to check the mu and theta limits. And we also looked at one more today. Yeah, the third thing we looked at was how to how to design for, at least an introduction to design for roof beams, and we've spent quite a bit of time on that as well. So quite a variety of topics that we have covered over the past 2 days. And yeah.